yeah, if anyone wants help choosing classes, I can give advice on that. I used to do that in my smaller classes where we discuss, what classes people want to take, whether that's, advanced double E selectives, other electives, the engineering breadth requirement, so on and so forth. I like advising people on classes. Though as I get older, my knowledge gets less and less relevant. Really? Most people I know did not like MSc 230. So maybe they have a different professor teaching it nowadays. Aubrey, your name isn't showing up in the participants list. Your still show is your 270 exam name. Thank you. I mean, I took ME 270 as my engineering breadth requirement. So I took mechanical engineering statics. It's a class that I think is, you have to be fairly diligent to excel in. It's mostly just high school level physics. And it's really hard to stand out in that class. But at the same time, like I think as long as you pay attention, you don't really fall behind or anything like that. So ME 270. The nuclear engineering ones are known to be fairly enjoyable, different topics, something that's fairly unique to Purdue. So is it Nuke 200 or is it Nuke 273? I forget that they asked you to take, but nuclear is a good one too. There's certain ones that I recommend no one ever take. Don't take CHE 205, the chemical engineering one. that's probably not a good one to take. It's like calculations in chemical engineering. Let me see if I can bring up engineering breadth. Engineering, Purdue EDU, academics, undergraduates, degree information, engineering breadth requirement. Yeah, CHA 205 is chemical engineering calculations. Don't take ME 200 thermo. What else? I had one friend that tried to take ME 413 noise control, said it wasn't that useful and wasn't worth it. There's some unusual options like IE 335 optimizations, operations research, and IE 336 stochastic models. You can only take those after you have 302 if you're an ECE student, or you have to take earlier classes in the IE chain if you're doing like an industrial engineering minor. I heard those are useful depending on what you want to get into. There's the triple E classes, which are, and they're civil engineering counterparts. So there's like CE/triple E 350, CE/triple E 355. Not too demanding. I didn't even notice they added ABE 201 now, thermodynamics and biological systems. Probably not what you want to take. And BME 201, biomolecules. Interesting. Didn't have those options when I was young. I took ME 270. I was also a physics minor. So when it comes to the science selectives, I did all the physics ones. Well, not all the physics ones. I could never get into like intermediate mechanics. So I took intermediate optics, modern physics, which was 342, and I did another class to round out my minor. Favorite undergrad math class? Oh, I guess we're doing some biographical information today. Probably Math 266 with Professor Johnny Brown. Johnny Brown's really good. Most of the time he teaches Calc 3, I think, but he was really good at differential equations. Let's see. I was in a smaller section. I was in smaller classes because I took accelerated calculus 2 and accelerated calculus 3, which, they only offer like in fall and spring respectively of your freshman year. So they weren't the full-on honors version, but they were for like more, I guess, quote unquote, more prepared students. So I didn't take. So I took Math 173 and Math 174. I don't even know if they exist anymore. I took Math 351 instead of Math 265. So I wanted a little bit more proof emphasis in math. So, Math 351 is a good one. Yeah, I also had, I had a visiting prof for Math 173, which is my accelerated Calc 2. I had a visiting professor, I think, for 174. And I definitely had a visiting professor for Math 351. He was Scottish, so he had this amazing accent. So, yeah, I don't know. My advice is, if you feel like you've been burned by having large lecture hall style math classes, definitely, challenge yourself to take a harder math class, and sometimes you get a better experience overall. So that's my advice when it comes to math at Purdue. Which one is 416? Is that complex analysis? Oh, probability. Oh, like stats 416. Ooh. See, my personal advice is don't bother taking a stats class until you've had 302. This was advice my advisor once gave to me. Don't bother taking a stats class until after you've had 302. And then if you still are like, wait a minute, I love more probability, I need more probability in my life, then you can take another stats class. Right. I mean, AJ, you're kind of doing things backwards, but yeah. We already have stats in our curriculum. It's the same reason, like, you don't tell computer engineers to take like a discrete math class besides 369. If you like, man, I want more discrete math and abstract algebra, then you, after 369, you take another class. I mean, it's 302, ECE 302 is continuous probability. So you do need integrals and such. Like, it's not like counting problems or anything like that. So that throws a lot of people for a loop. Depending on who you get, depends on how rigorous it is. All right. Any final course questions? I want to get started. Oh, do you think I should include this discussion about courses in the actual lecture proper, or should I in the recording, or not? Or should this be a benefit of attending in person? No? Okay. One says no, one says yes. Leaning towards no. 3 say yes. May as well. Okay. I'll have to really listen carefully when I edit. All right. Good morning, ECE 20002 class. By vote of the class, I'm going to include some of the preliminary discussion about, courses to take at Purdue, just some unsolicited advice I've been giving about what to do for courses. So I'm going to include a lot of that in the recording. Onto our current topic, of class today. We're going to finish out talking about real components, start talking about transmission lines. Our goal is to get through lecture set 8 by end of tomorrow, so we'll see how far we get. If not, I might just cut it off and say no more new material. Don't forget, quiz 5 is due on Saturday, 11:59 p.m. It'll be the final quiz. Don't want to forget it. It's going to cover stuff from lecture set 6 up until lecture set 8. So anywhere from low frequency response to single transistor amplifiers up until real components like today. Lastly, I can't remember if I've said this to everyone, but I won't be coming back to teach this class anymore. Let my materials live on and help other people. If you ever need help with this material later, feel free to shoot me an email and I will do my best to help out. Students now, students forever. I haven't formally accepted this yet, but my plan is to actually teach an EPICS class in the fall. There wasn't any room for me to teach an ECE, so I'm thinking about teaching an EPICS class in the fall. And then after the final exam, I might release some additional fun materials, whether that's bonus lecture sets or diagrams or things like that. I don't know. The position I have on offer in EPICS has me supervising 3 teams where I'm replacing someone that just left, and as an advisor, I was told the project would be more heavily hardware and a little bit software based. So figure out relevant EPICS projects ahead of time. I don't know. I can do that. Riyadh, what do you mean by JSET lectures? Oh, okay. Yeah, imaginary numbered lectures. I might actually do a negative numbered lecture just to throw everyone off. So that'd be material that's considered prerequisite for this class. I don't know if I'll have time to get lecture set J6 ready on 2 ports. And if you can, you're always welcome to suggest more topics if there's a circuits related thing you want to learn about that you've heard about and haven't done. So like Telegrapher's theorem or other things. Yeah, I haven't figured out what a complex valued with real and imaginary components lecture set would mean. I think it would be after the real numbered, but like builds off of it in a tangential way. Can't figure that out. All right. I procrastinated enough. Time to share my screen. So we were talking about our real models of resistors, inductors, and capacitors, and specifically for inductors and capacitors, we talk about an element quality factor, which is the reactive part over the resistive part. So here we say that for an inductor, for a given frequency, the element quality factor is omega L over R sub S. And then for a quality factor for capacitors, 1 over omega times R sub P times C. Where R sub S is the series resistance of the simplified model of the inductor. And then R sub P is the parallel resistance in the simplified model of the capacitor. And then we looked at, okay, if we did a simplified model with a parallel R, L, and C, we get something that looks like this, where we can source transform this so that we get a parallel resistance, but we still have this, series resistance that we don't want to deal with the inductance. And then similarly, when we do a series RLC circuit where we've got, R, L, and C, again, not bothering with a more complicated model for the resistor. This is all in series except for these parallel components right here. If only we could put them in series. And that's where we come up with single frequency impedance conversion. So for one frequency only, you can convert parallel elements into series ones and series elements into parallel ones. So the way we did this was with the series to parallel conversion, where we say, okay, the parallel conductance is the resistance over resistance squared plus reactance squared, and the parallel susceptance is negative the series reactance over the resistance squared plus the reactance squared. And then by duality, you get something very similar for what the series resistance would be and the series reactance would be given a parallel conductance and parallel susceptance. So these are the formulas. Let's see how they apply to our non-ideal inductor and non-ideal capacitor. So we wanted to convert the series resistance here so that we had all, or series resistance and inductance here so that we had all elements in parallel. When we do that, we are going to note, okay, X sub S is omega times L sub S. And we're going to get, B sub P is -1 over omega L sub P. Remember, it's normally the admittance of an inductor is 1 over J omega LP using J terminology and phasor terminology. However, 1 over J produces a negative sign, so that's why there's a negative sign with the susceptance. So we work this out. So we say, okay, the parallel conductance is RS over RS squared plus omega LS quantity squared. We factor an RS out of the denominator. So we get something that looks like this. And we go from having an RS in the numerator to an RS in the denominator because we factored out the RS squared. And then we notice, wait a minute, this right here is the element quality factor. So we'll get that the conductance is 1 over the resistance, all divided by 1 plus QZL squared. So we say that the new parallel resistance is just the series resistance times a factor of 1 plus QZL squared. So this is going to get bigger, much bigger. So if we have a quality factor of just 10, this is bigger by a factor of 101. That's significant. Now, the parallel inductance, so we're going to say plug in into this formula right here. So we'll get negative omega L sub S over R squared plus omega L sub S squared. We'll do the same trick. Now we'll factor out an omega L sub S squared. So we'll get RS squared over omega L S squared. Okay, these squares shouldn't be there. I didn't do this properly when I was making these slides. The inside square shouldn't be there. You just need the outside square. And then we'll get equals -1 over omega LS over 1 plus 1 over QZL quantity squared. Now, for reasons that are a little bit beyond us, it's convenient to keep an inductance and an inductance when we go from series to parallel. We don't want to change the inductance into a capacitance. So we leave things in this form and we say, okay, this B sub P is equal to the parallel inductance, the series inductance, divided by, or I guess multiplied by 1 plus 1 over QZL's quantity squared. So this is what happens when you just match terms here and here. So notice if we put in a quality factor of 10, we get that the parallel inductance is the series inductance times 1 plus 1/100th, so 1.01 times LS. So basically, the parallel inductance stays very similar to the series inductance, hardly changes. And that leads us to make some observations for the high Q factor inductor. So in the high Q case, so with our rule of thumb, we say that the quality factor greater than 10. The parallel resistance, well, we don't really need to bother with this 1 plus, something that's, bigger than 100. It's just, the series resistance times QZL squared. Likely large enough to avoid altering the resistance of the surrounding circuit. Because remember, if you have a large parallel resistance, its effect is hardly noticeable. In the high Q case, the parallel inductance is just basically the same as the series inductance. There's also this weird trick that comes into play. Say you're in a situation where you know the inductance and you know the quality factor. If the original series resistance is unknown, you can still approximate the parallel resistance directly from the known Q. So in the high quality factor case, you'll get R sub P, which is normally RS times, QZL squared, is going to be QZL times omega L, where we turned QZL, which is omega L over RS, into one of them into an omega L, and the other QZL sticks around. So this approximation is worth noting right here. So mark that a little bit more, make that a little bit more visible in your notes. So even if you don't know the original series resistance, you can approximate the parallel resistance directly, as long as you know the Q factor. Kind of neat. And of course, we're assuming we're using the Q factor, which is the one at the natural frequency. So let's apply the same process to our capacitor. So we're going to do a parallel series conversion on the simplified capacitor model with R sub P, noting that G sub P is just 1 over R sub P, and C sub P, or B sub P, the parallel susceptance is omega C sub P, to produce RS and C sub S, where X sub S is -1 over omega CS. And this works out very similarly. So, you use the parallel to series conversion formula, factor out the G sub P squared, and you're like, wait a minute. This is 1 plus QZC squared. So because this is in the denominator, you'll get R sub S is R sub P over 1 plus QZ sub C squared. And then the capacitance, when you work out all the steps, is C sub P 1 plus 1 over QZ sub C squared. So notice RS ends up being quite a bit smaller than R sub P, and C sub S will stay basically the same. So if Q sub Z is 10, this is 1.01 times C sub P, and then RS is just going to be 1/101st of R sub P. Yep, series resistance just simplified to RP over Q sub Z sub, or QZC squared. So a small series resistance is barely noticeable. It's likely small enough to avoid altering the resistance of the surrounding circuit, because a small series resistance, basically gets closer and closer to a short circuit. And a series capacitance is basically unchanged. And then just like even if you don't know the original parallel resistance, you could approximate the series resistance directly from a known Q, as RS is equal to 1 over QZC omega naught C. What questions do we have? Are we ready for an example? Oh boy, that's enthusiasm. One person out of 26 is like, yes, we want an example. I appreciate that. So here on slide 21, we'll have the example. So we'll have that series RLC circuit from before where we're using the simplified model for the inductor, simplified model for the capacitor, and just the plain old R for the resistor with a Thevenin source. So find all the bandpass circuit quantities that we would normally associate with an RLC circuit. So the center frequency omega sub m, B sub omega, the bandwidth, omega L, the lower half power frequency, omega H, the upper 3 dB frequency, and the overall quality factor Q for the circuit, given the following information. RS is, let's make it 40 ohms, and R, let's make it actually 100 ohms. And then L is equal to 20 millihenry. QZL of omega naught at omega naught is equal to 40. The capacitance is 0.05 microfarads, so a fairly small capacitor. And the quality factor of the capacitor at the natural frequency is 100. So normally when we talk about a series RLC circuit, the resonant frequency is the same as the natural frequency is the same as the center frequency. However, now we don't have a purely series circuit. We've got, this little parallel bit right here with R sub C and the capacitance. So we're going to have to make an assumption. And there really isn't an easier way to solve this problem other than making the assumption at the start. So the assumption is that the natural frequency is just 1 over square root of LC, even though it may not be the case for this circuit. Why can we do this? Note well that both components meet the high Q rule of thumb. So both components have a Q greater than 10. One was 40, one was 100. So we expect the center frequency to be approximately the natural frequency, 1 over square root LC. So you get square root of 10 times 10 to the 4th radians per second. If you work out the math, about 3.16228 times 10 to the 4th radians per second. Okay, quick, without looking. 3 factorial, oh my goodness. Without looking, what's a good engineering approximation for the square root of 10? Mathematicians hate it when you do this, but what's a good engineering approximation for the square root of 10? I've seen 3.1, 3.2, 3.3, 3.33. 3.33 is getting at it, so you could say it's 10/3. So there's some sort of duality between 10s and 3s. Salem has it right, pi. Very good. So engineers will cancel the square root of 10 over pi to 1. And in fact, on slide rules, they used to mark pi and basically treat it like it was the square root of 10. Because the difference between 3.14159 and 3.16228 is, less than 1% error. It's about 0.5% error. You understand why they got that? I mean, it just happens to be the case that square root of pi and 10 are very close to each other. Okay, if you don't like that, you don't have to do whatever, but it's just a nice little trick that you don't teach people like us anymore. So apply single frequency parallel to series conversion on the simplified capacitor model. So we have all the formulas. So we say that C becomes C sub S, which is 0.05 microfarads times 1 plus 1 over 100 squared, which is basically still 0.05 microfarads. And RC, we can estimate using this estimation formula without having to bother getting R sub P. So we get quality factor, 1 over quality factor omega naught C. So we get 6.32456 ohms. A pretty small resistance. Now, we didn't get what R sub L was, so we have to estimate it from the quality factor too. So remember, R sub L, little r sub L, is, equal to, go back to the ideal inductor case. So the series one is equal to the parallel one divided by 1 plus the quality factor squared, using our formula. And then we can write the parallel one using the approximation formula, QZL omega naught L over 1 plus QZ squared. So we'll get omega naught L over QZL, which is 15.8111 or 8114 ohms. So this is probably the step that throws the most people off. We're using the impedance conversion formulas, even though we aren't trying to convert this impedance. All we're trying to do is estimate the series resistance using the inductance and the quality factor at the resonant frequency that we approximated. So there's a lot of levels of approximation going on right here, but it's good enough for this problem. Single frequency impedance conversion is already an approximation at a single frequency. And then we don't need any sort of source transformation to put everything in series. Everything will be in series. So we get the circuit right here. So we get RC comma S and C sub S right here. Everything in series. And note, we've got 4 resistances all in series. So we'll define a new resistance equal to the series combination of all resistances present. So R new is RS plus R sub L plus RCS plus big R. Using those new values that I gave you, should get 162.136 ohms. I had to really massage this problem, all right, to get sensible answers for this next part. So using R new, L, and C sub S, we have a series RLC circuit. Use all those old formulas we got for resonant series. So we'll say the center frequency is equal to the natural frequency, which is that 3.16 times 10 to the 4th radians per second. The bandwidth is just R nu over L, 4.11 times 10 to the 3rd radians per second. We'll use the symmetric approximation for a high Q circuit. Omega L is just the center frequency minus half the bandwidth. The upper 3 dB frequency is the center frequency plus half the bandwidth. And the quality factor is just omega M over the bandwidth, which is 7.70. So notice, even though we used very high quality components, 40 and 100, the overall circuit, because of the other series resistances involved, really lowered our quality factor to below 10. So is this really a high quality circuit anymore? Not really, according to our rule of thumb. So you might say, well, maybe this first approximation isn't going to hold. So this is where you would verify with a SPICE circuit simulation for a moderate Q circuit. What questions do we have? No questions? Okay, time to move on to transmission lines. Something that makes me a little bit excited. We get to talk about this. This wasn't part of the original curriculum for the class that I took as my version of 2002. It just showed up in later classes like 4 different times. So now we're at least giving you a first exposure here. So what is a transmission line? So a transmission line, abbreviated as TX line. TX is the abbreviation for transmission, or as a TL, just, initialism, transmission line. It's a specialized structure that conducts electromagnetic waves in a contained manner. So we use transmission line to denote cables or conductors for which the wave nature of electromagnetism must be considered, leaving the realm of lump circuits behind for distributed circuits. Everything we've studied so far has been a lump circuit. where you could basically say there is one point in space, across time, where this resistor behaves like a resistor. It doesn't matter how close you zoom in or how far away you zoom out. All the resistance is in a single point in your circuit diagram. It doesn't matter what length scales are involved. Same with capacitors, inductors, and op amps and other things. Now we're going to talk about distributed circuits, where you must consider the fact that there is a certain resistance per unit length and a certain capacitance per unit length involved here. So because of that, you're going to get a different behavior than you would if you considered all of the resistances and inductances as being in a single point and all the capacitances and conductances being in another point. So this means that for the first time, the length of the transmission line dictates the validity of the model. So we can use lump circuits to approximate any distributed circuit where the parameters are done and just treat wires like wires with their own lumped parasitics. But that's going to depend on the length of the line. And we've never really had to consider length as an electrical quantity before. We don't work in meters. That's like the realm of mechanical engineering. But now we do have to consider it. We'll compare the length to the wavelength of the signal. So we'll have to compare the length L of our wire to the lambda, which is the wavelength, which is C divided by the frequency, which is 2 pi C divided by omega, where omega is radio frequency, and C is 299,792,458 meters per second, exactly the speed of light in a vacuum. So common types of transmission lines are planar lines, like you consider microstrip or strip line on a printed circuit board. Twin lead cable, which is 2 cables held apart by plastic spacers at a set distance. There's twisted pair cable, where the cables are in contact and twisted against each other. And then coaxial cable, another invention of Oliver Heaviside. So we're going to consider this incremental section of transmission line right here and talk about primary line constants. So at a point, V of Z and T, where we're talking about a position Z and a time T, and the current IZ of T, I of Z and T, we're going to see an incremental amount of resistance over incremental length delta Z, an incremental amount of inductance over length delta Z, an incremental amount of capacitance, length delta Z, and then an incremental amount of conductance, remember 1 over resistance, delta Z. Such that at the other end, we're going to get a new V of Z plus delta Z T and I of Z plus delta Z T. Because the current changed because we're peeling current off through the shunt elements, the capacitance and conductance, and where the voltage changed because there's going to be a voltage drop across the series resistance and line inductance. So we'll call series resistance per unit length R subscript L, and then we'll have L subscript L, series inductance per unit length, shunt capacitance per unit length, C sub L, and then G sub L for shunt conductance per unit length. Now, unlike your book, I like to put subscripts L here. Some books use a prime notation because these aren't in units of resistance. They're in units of resistance per unit length. So this is in ohms per meter, Henrys per meter, farads per meter, Siemens per meter. So this just helps me keep track of my units a little bit better. If you actually want to calculate what these should be for a given geometry or figure out interpretations of what these are, you're going to have to take an electromagnetics course. So take ECE 30411 or its sequel 30412, which if you're an electrical engineer, you have to take 30411. So this would be the time to learn more about transmission lines. And one comment. Now you might say, okay, well, this is good for an incremental amount of length. What if I have, something that's like, 100 lengths of these long? Can't I just say it's RLCG and then another RLCG, 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 so on 100 times? Well, the answer is no. No finite number of delta Z length segments will fully capture the effects exhibited by long lines. So you'd have to have an infinite number of segments to get the full effects of time delay and what it does to the voltage and the current. So we're going to take R sub L and LL, CL, and GL as givens. Questions? Dude, his name is Oliver Heaviside. I mean, I am saying that the relationship won't be linear in the end. If you have a long enough wire, you don't get a purely linear relationship where you can just multiply by the length of the line. We'll see that later today or tomorrow. Yeah, shunt is the fast track to ground. So yeah, basically, when we talk about series or line things, we talk about things that are basically in this sort of series configuration, and shunt means between two lines, like a parallel configuration. So that's kind of, it's, we talk about line resistance or line inductance, and then shunt capacitance and shunt conductance, where we really mean a series, parallel, parallel. But parallel with respect to what, it's kind of a way to get around the parallel to what, or in series with what. They're in series with each other. They're in parallel to each other. Nope. Nowhere do we have to introduce ground. Yes, there are dedicated signals for transmission lines. They kind of look like coaxial cable or just a box. I don't like any of the symbols really, but you can find them on Wikipedia. It's more important to understand it mathematically than I think it is to have a good circuit symbol. And the thing is, if you have a circuit symbol, how do you label it? Do you label it with your primary line constants, or do you label it with the secondary line constants we'll talk about later? Like, you have to label it with a lot of constants. So like, you're not summarizing it's hard to summarize all the information of a transmission line into a schematic. So let's take a little before we take a detour, let's talk about the skin effect, a big detour. So just so you know, the DC series resistance of a transmission line is normally quite small, except when you have really long wires. Because remember, resistance is L over sigma A. So if you have a really long length of line or just a really skinny cross section, you'll get a big resistance. However, the AC series resistance differs from the DC series resistance, something that we wouldn't expect based off of anything we've covered so far. And you'd have to talk about this a little bit more in electromagnetics class or something like that. But as you increase the frequency, there's a local magnetic field generated around a wire that forces the current towards the surface, in other words, the skin of the conductor. The cross-sectional area that the current flows through decreases because instead of flowing through the whole circle, it's now flowing through basically an annular cross-section where there's a hole in the middle. So there's an increase in resistance. So there's a skin depth little delta as the distance beneath the surface of the conductor where about 86% of the current flows for a given frequency. We're not going to work with skin depth calculations. They're not really topical to this course, but this is called the skin effect, where the AC resistance is bigger than your DC resistance because of a change in the distribution of where current flows in a conductor. So the skin effect is one reason why high frequency signals travel over stranded wires instead of solid ones. So if you have a stranded wire, instead of having one big wire where most of the current doesn't flow in the middle, you have a bunch of little wires where the current flows through most of the wire instead. The other reason why you want a stranded wire is flexibility. It's easier to twist the cable, bend it into the shape that it needs to be without breaking. Okay. But one thing I think your book doesn't do a good job of is presenting models of the transmission line. Let's say you have a very short length of wire. So like we've been assuming all along where all wires are short. How would you model the parasitics of a wire? Well, you'd probably do something like this, where you'd say, here we're going to have z equals 0, and here we have z equals positive L, the length of the line. If the length of the line is less than a 60th of the wavelength for the frequency you're considering, the effects of C sub L and G sub L are pretty negligible for realistic values that you would get. So what you do is you represent the transmission line with just a lump series resistance, a single section of RL sub L, or R sub L times L, and then L sub L times L. Say that 5 times fast. So this is just a single resistance and a single inductance for a very short length of line. So all you have to consider is the wire behaves as though there's a parasitic resistance and inductance. We talked about the leads of our realistic components, the leads of a capacitor, the leads of a resistor. This is kind of what we're talking about. Notice that for this simple model, the voltage on the left at V0 of t and V of LT are not the same, but because this model is so simple, I of 0t and I of LT are the same, because there's nothing that changes the current along this top conductor, or I guess this top branch. What if we are dealing with a longer line? Well, we have this sort of medium length transmission line where we go from the series model to a so-called nominal pi model. So between a 60th of a wavelength and a 20th of a wavelength, the effects of all primary line constants are notable. So here we're going to have a sort of half of the conductance, half of the capacitance, the entire resistance, entire inductance, half of the capacitance, and then half of the conductance per unit length times the length here, in between z equals 0 and z equals L. So what we're going to do is, take the Laplace transform of everything and say, okay, we'll say z right here is R sub L times S L sub L all times L. And then we'll lump our 2 halves of our shunt admittance into y over 2 is equal to 1/2 a quantity G sub L plus SC sub L times L. So notice this looks like a capital letter pi, hence the name nominal pi model. And in this model, the voltage at one side does not equal the voltage at the other, and the current at one side does not equal current at the other. So what we're saying is if you have a short length of line or a medium length of line, you can basically treat it like it's, this right here. As long as you don't care what happens in the middle of the line, you only care about what happens at 0 and z equals L, you'll be okay. Inductors very, very small skin area and cross section. Then you'll get a very high resistance to them. Do you have any questions about these sort of so-called, simple models for transmission lines? Why is there a positive and a negative? A positive and a negative where? I don't see it. Why there's a plus sign? I mean, these are differential voltages. So like we're saying the voltage between this bottom conductor and the top, the voltage between this bottom conductor and the top differs over a length of line. So you might ask, okay, what about if we have a long transmission line greater than a 20th of a wavelength? Well, that's what we're going to spend the next let's see, 16 slides trying to do. Wait 16 slides for long TX line. So we need to take a detour now and talk about the wave equation. So the wave equation is the simplest second order hyperbolic differential equation. So by hyperbolic, it's a type of partial differential equation, so one where the function depends on two variables instead of just one. So it basically says the second derivative with respect to time of a function of position and time equals v squared times the second derivative with respect to position of a function of position and time. So it relates the second derivatives through a constant where the positive real number v is the speed of the wave. So we will see that the voltage and current separately obey a general wave equation in transmission line. And then we're going to deal with more generalized wave equations where there's a first derivative term with respect to time. So in other words, partial of f of z of t with respect to t, leading to attenuation / damping of the wave. So, this is an undamped wave that will just continue propagating forever in one direction or forever in the other direction. We will deal with waves where they attenuate over time as well. So let's jump right in and see if we can derive what are called the Telegrapher's equations. So we'll say Vz of t minus Vz plus delta z of t. If we go back to our incremental transmission line, so how does the voltage change from the left side to the right side? Well, it's Vz of t minus RL delta z minus L sub L delta t plus Vz plus delta z of t equals 0. So moving it to the other side, Vz of t minus Vz plus delta z of t equals L sub L delta z, partial of I with respect to t plus RL delta z I z of t. I of z and t. Oh, so many variables. So this is just KVL right here, relating the two voltages at the different sides of the transmission line to the differential equation representing the voltage drop. So it's RL times its incremental length times the current plus L sub L times incremental length times the derivative of the current with respect to time. Now we're going to take the limit as delta z goes to 0. Because we dealt with an incremental length, now we need to deal with an infinitesimal length, infinitesimal instead of finite incremental. So what we can do is divide both sides by delta z, and we notice that this right here looks like the definition of a derivative, except the difference is backwards. So this looks like the definition of the partial derivative with respect to z, except backwards. So we need a negative sign. So by leaning on what we know about multivariable calculus, so math 261 or whatever equivalent you took, we'll get that the partial derivative of v of z of t with respect to z equals negative L sub L partial of I z of t with respect to t minus R sub L I z of t. So now we have this, partial differential equation in two terms, v of z of t and I of z of t. Excuse me for a moment. Oh, allergies are bad today. So we can do the exact same thing using KCL on right here. So we'll get I z of t into this node right here minus I of z plus delta z of t equals the current that flows down through this capacitor, CL delta z times dv of z of t dt, and then GL delta z times v of z of t. And sure enough, we get here. Now you might say this should really be z plus delta z, but we're taking the limit as delta z goes to 0 anyway, so it doesn't really matter. So I guess limit as delta z goes to 0 of v of z plus delta z of t equals v of z of t. And then we do the exact same trick. We divide both sides by delta z, take the limit. Notice it's the same as the partial derivative. And we get this comparable equation right here, the other telegrapher's equation. The partial of I with respect to z is equal to negative CL partial of v with respect to t minus GL times v with respect to t. Or GL times v as is. Are you with me so far? Remember, lambda is always c divided by f, or 2 pi c divided by omega. So for a given frequency, you can always calculate the wavelength just by a reciprocal relationship with the speed of light. So here are the full telegrapher's equations. So what we're going to do is take this equation, take the derivative with respect to z again. So we'll get a second partial derivative with respect to z equals this mixed derivative of I with L sub L and I equals this first derivative with respect to z of R sub L of z. And we can do the same with the other partial, and we can also take this equation and now differentiate with respect to time. And so we can get something that we can plug into here. And then this equation is just this equation down here. So we can get something where we substitute all of the partial derivatives with respect to I with things in terms of voltage. And you get this equation right here, which is a little scary, but the big thing is it's a generalized wave equation. The partial with respect to z squared of voltage is L sub L C sub L times the partial with respect to time of v plus quantity GL LL plus RL CL time close quantity times partial with respect to time voltage is plus RL GL times voltage itself. I could do the exact same work, except, now you take partial derivatives, this one with respect to z, this one with respect to time, and you can get an similar equation for voltage or current. Or second partial with respect to z, second partial with respect to time, first partial with respect to time, and then current itself. These are generalized wave equations that show that, voltage and current propagate as a wave along transmission lines. So maybe we want a simpler way of writing them because these are kind of scary looking. So we can take the Laplace transform of the two telegraphers equation and ignore all initial conditions. And remember, by the time derivative property of the Laplace transform, a derivative with respect to time is just s times the variable for getting initial conditions. Second derivative with respect to time is just s squared times the variable. So defining propagation parameter lowercase gamma is square root of the quantity RL plus SLL close quantity times quantity GL plus SCL close quantity. And characteristic impedance, Z naught is equal to square root of RL plus SLL over GL plus SCL. We get this much simpler form of the differential equation using propagation parameter, where partial with respect to Z squared of voltage is just gamma squared times voltage in the S domain, and similarly for the current. So it's a much simpler partial differential equation to deal with. Do we have any questions? If not, I will see you tomorrow for our final lecture of new material. Goodbye, everyone. You're welcome. You're welcome.